Thank you for coming. Good afternoon. My name is Mark Sever. I'm global application expert in Danfoss, and my main focus are food retail systems and particularly CO₂ systems. I will present you today one real case. We had one Danish supermarket where we implemented a heat recovery unit from Danfoss, where we did quite substantial savings in, let's say, consuming additional energy from the district heating system. This is a real plant, many in Denmark, where we had a chance to analyze system behavior with and without heat recovery unit, because originally plant was connected to the district heating, and all the heating was consumed from the district heating system. As a second phase, end user decided, let's try to do this heat recovery system and see what will be performance. So we had 1 year with heat recovery unit, and before we did a whole year analyze without heat recovery unit. And we get to these fantastic results that we almost didn't have a need for this additional heat from the district heating system. But how we did it? So first of all, some basics about heat recovery. When we don't have a heat recovery request in the system, what we are doing, of course, we are doing in a way to optimize operation of refrigeration system, not consume so much energy for the compressors, etc. But if there is a need for heating, of course, we have to do something. First step is to increase pressure. And by increasing pressure, we are, of course, enabling more and more heat to be recovered. As a second phase, we are able to increase the reference temperature out of the gas cooler to get at the end of this maximum requested stage to this what we call optimum COP line. And in that way, we can completely recover heat from the refrigeration system. How it works in the real life. So if we have a, let's say, here is a heat recovery, let's say, plate heat exchanger. At the first stage, when there is no heat recovery request, there is only very small potential what you can recover, because the temperature what is on the discharge of compressors is very low. And if we assume that the return temperature from the system is on the level of 27 to 28 degrees Celsius, this line of isotherm of 32 degrees Celsius is simply limiting how much we can recover. So as you can see here, it's on the level of 10% of the available enthalpy difference. The rest of the enthalpy difference we have to release to the ambient, of course, using gas cooler. When we need to do heat recovery, as I said, first step is to increase the pressure in the system, gradually, of course. And if you can see here, potential enthalpy difference, what you can recover, is becoming more and more. And our final goal is to get to the level which is above the critical point. Typically, it's around 80 bars. Keeping at the first time, the constant temperature, what we started is, this case, it is 9 degrees Celsius, but it could be 5 degrees, it could be 15 degrees, depending on what is the ambient conditions. But this is the goal, to recover this heat. You see this red line. But still, the rest of the heat, what we have to release, we are using fans on the gas cooler. What to do next? So this is the point when still refrigeration system has a acceptable efficiency. But again, if you need to produce more heat, of course, you need to engage your compressors more and more. And how to do it? We are starting to decrease the speed on the fan. And by doing this reference temperature out of the gas cooler is becoming higher and higher. But again, we have to stop at some point, and the point is this optimum COP line. When we get to this line, we are as a final stage what we can do with these pressure temperatures. And this is the point where we can completely recover heat in the heating system. of course, now our refrigeration system is not super efficient because actually we are working like in the summertime because the reference is quite high, 32 degrees Celsius, pressure is 80 bars. We have quite a lot of this gas fraction in the receiver where we have to bypass. So, of course, the goal is to produce more heat. So this is the reason why we are doing all this process. And the point is, it's working part of the system like a heat pump. What is from the other side, from the hydronic side? So this is our heat recovery unit. There are a lot of versions of this. This is a version of 2-tank solution, what we used in this plant. So you can imagine from this side, heat is coming to these big vessels. Above is the heating, what we have to supply to the users. And if there is not enough heat stored in these tanks or heat produced from the CO2 systems, there is also possibility that you can connect to some external heat source. In our case, it was district heating, but it could be any other boiler system or gas station or whatever. There is also an option, but not used in this case, to sell the heat to the district heating. This is something what it has to be, of course, dealt with the district heating systems to enable this possibility. And in some countries, they found it as a quite interesting feature because also the district heating has some period in the year where they have to do this servicing, etc. So they consider this as a supply to their heating system and to overcome this service situation. But in our case, we had this connection to this district heating system. And how it works. So on the right side, it's this heat recovery unit, what we had in our system. On the left side, it's our refrigeration system. And as you can see here, we have 2 controllers. ECL controller is controlling everything what is on this hydronic side happening. Everything what is on the CO2 side, it's deal with our PEC controller. But based on the measurements here, the ECL controller is sending signal to the PEC controller, do this process what I tried to explain before. So, as I said, we are following this logic, and by increasing request from the ECL controller to the PEC controller, we are starting to do this process, of course, in a controlled way. First, we are increasing pressure. After pressure is increased to the level what we said in my example, it is 80 bars. We are getting to the heat recovery pressure in the gas cooler. And then as the last stage, as I said, we are increasing pressure, temperature reference for the temperature out of the gas cooler. And then we are reaching this point here in this triangle. Very often it's a problem in the winter time when you need a lot of heating. Your refrigeration system is mostly on the minimum. And then there is no enough, let's say, heat sink to produce more heat. And in many cases, especially in this Central European climate, it's necessary to add additional evaporator, which will be engaged as a very last stage in this heat recovery process to enable this heat pump operation so that your compressors will work more and more, and of course, to produce more heating energy. So, this is something what is happening at the very last stage. First, we are bypassing gas cooler completely so that there is no any more flow through the gas cooler, because even you stop your fans simply by going through these cold coils, you will overcool your CO2. It will become liquid. And then as a very last stage, we are able to engage this additional false load evaporator. The second or the third, let's say, important thing is something what is happening on the hydronic side. It's this importance of return water temperature limitation. If you can imagine you are doing your heating system and you are not controlling what is your return temperature coming to your, let's say, in this case, heat recovery unit, what is coming on this plate heat exchanger. And then, for example, you have return temperature of 40 degrees Celsius. If it's 40 degrees Celsius, simply you have some thermodynamical limitations, so you cannot cool with 40 degrees temperature water. You cannot cool down to, let's say, for example, 32 degrees. It's impossible. So what is a strategy? First, you have to limit on your consumers. There are balancing valves in the system, automatic balancing valves. You can define what is the designed flow for this particular point. There are valves, we can do it. And then on the top, you can also put a very smart driver to limit this temperature. So you have some temperature measurements that can control what you will allow to have as a return temperature. In our case, I use this example with 27 degrees Celsius, and let's say typically the ideal system is with this 27, 28 degrees Celsius return temperature. I try to show this in log pH diagram, that if we imagine on this plate heat exchanger of this 5 Kelvin's temperature difference, which is a good example, you can make this complete heat recovery. But the problem is, if this return temperature is on a level of 32 degrees Celsius, just 5 Kelvins more than what is, let's say, ideal situation, what is happening? 32 plus 5 degrees Kelvin's difference for the plate heat exchanger will result in this 37 degrees option, what you can extract on your plate heat exchanger. And you can see here that the enthalpy difference, what you can use for the heat recovery drastically change, just for this 5 Kelvin's temperature difference. And what is the reason? The reason is that the isotherms in this area are very stretched. So no matter what, 5 Kelvins doesn't sound so much, but if you are on the more, let's say, left on this log pH diagram, these curves are very close. But if you are getting to this area where you are, let's say, above the critical point, these isotherm curves are really stretched. So the availability of the enthalpy difference, what you can utilize for heating the water, drastically dropped. In this case, it's you lose 35% availability to recover. Then what to do? The rest you have to again release to the ambient, and this is what is definitely not your goal. How to do it? There are valves, ABQM valves. It's automatic balancing valves. On these valves you can limit the flow, and it will work, of course, what is necessary to do. But on top of this, the point is to put these smart drives together with sensors, and then if you program it in the right way, of course, you will get this possibility to either control the temperature limitation, so it can be really controlled on, let's say, 27, 28 degrees, or you can just limit, and then everything what is below 27, you allow it, but you are not allowing to go above this temperature. This is example of the thermometer from this plant to show that it was really achieved this goal. Final results. As I said, we had a fantastic opportunity to have one whole year measurements when the system was connected to the district heating. And then the year after, it was connected to our heat recovery unit. And if you can observe, during this month, of course, the heating requests changed definitely a lot. With this gray bar, you see how much we can produce and how much we consume. And after all this year analysis, what is here presented, we can say that we saved in that way quite substantial tons of CO₂, which was supposed to be used if you use a burning plant. And in this case, it was used, of course, for the district heating. Conclusions. We did, first of all, analysis of existing system. And actually, most of the savings, what we achieved, was because we properly balanced the system and we applied this correct control temperature of the return temperature, and substantial amount of this savings was coming from that part. The rest, of course, is something what we utilize this heat recovery unit, and together all this give us fantastic results that this system was almost independent from the district heating supply. What can be done additionally? Of course, on this plant, there was not implemented this false load evaporator. So if you would like to be completely independent from any other heat source, there is also an option to add this element in the system, and then you will be completely independent from any other heat source, which is today quite interesting option. Yeah, that's it. Thank you very much for listening to me. If you have any questions, come to me or find me on the Danfoss booth. Thank you very much.